Okay, so finally, I guess we can start. Thank you very much for your patience. We had a few issues about technical things, but now we're happy that we can start with our webinar for today. Today we talk about non-alcoholic beer production, and I'm very happy to have a good friend from the University of Munich-Weihenstephan with me, Mr. Sönke Kienix. He is deeply in charge with the production of non-alcoholic beers at the Technical University Munich-Weihenstephan at the chair of Professor Becker. And you will start the presentation today about the production techniques, and afterwards I will follow up with a trial, with some results of trials that we have performed together. My name is Sandro Kaputza. I'm working for technical support and R&D at Hofsteiner, Germany, and I'll pick up your questions that you can put in the Q&A button anytime during the webinar at the end of the presentations, and then we can also follow up on your comments and questions that you might have. Okay, Sönke, the first 20 minutes is for you.
Thank you very much.
Yours. Feel free.
Okay, thank you, Sandro, for your introduction. Like you already said, my name is Sönke Kienix. I'm working at the TU Munich, Chair of Brew and Beverage Technology, and my main research topics are non-alcoholic beers and special reverse osmosis devices or reverse osmosis produced beers. And I think when we are talking about non-alcoholic beers today, what would be better to talk about some techniques. And this will be my honor today to present you. Before we start with the different production types, maybe let's talk about non-alcoholic beer and the consumption of non-alcoholic beer. In the last decades, non-alcoholic beer went extremely popular. It started all in the 70s, where it was only produced as I would say, a beer for drivers who were not able to drink normal alcoholic beers. But this mindset's completely changed. I brought you some data here. Around 200 people or 500 people were questioned around Munich why they are drinking beer or why they are drinking non-alcoholic beer and what they like about non-alcoholic beer. And until now, a very big percentage says that they drink non-alcoholic beer because they have to drive. But in the last decades, the convenience and the taste and the aroma of these non-alcoholic beers went more and more important for the drinkers and for the consumers. So nowadays, the quality, especially the taste and the aroma, the whole flavor of your non-alcoholic product is getting more and more important. And that's one of the reasons for the consumers to drink non-alcoholic beers. A part of the consumers drink non-alcoholic beer because it's extremely healthy. Without the ethanol, you have more or less non-toxic ingredients, I would say. And beer as itself has a lot of very healthy ingredients like different vitamins, biotin, etc., etc. So a lot of people drink non-alcoholic beers for sports drinks. When you compare non-alcoholic beer to different soft drinks, like lemonades, where the sugar content is very high, we have here a very healthy alternative with non-alcoholic beer. So it's considered as a clean label, it has a high health awareness, and of course, the taste and enjoyment and the social background when you're at different parties, for example, more and more people drink non-alcoholic beer. And that makes this product very, I would say, difficult for us brewers, because when we look at the consumer side and the, I would say, quality, it's getting more and more important. So for us brewers, this, the quality device is one of the most important things. So we have to focus on the demand for flavor and quality, and that leads us to some innovations. for some innovative, I would say, processes in the production of non-alcoholic beers, which I will present you in the following slides. The beer market, especially, well, the non-alcoholic beer market, is rapidly growing. During the last, or since the last 10 years, the market grew in Germany from 2% consumption of all beers up to 5%. So we have a very high increase of the consumption of non-alcoholic beers. And nowadays, when you look at Europe, especially, a lot of breweries are producing non-alcoholic beers. In Germany, in special, there are only a few breweries who are not producing, but most of the breweries, I would say, are producing non-alcoholic beers today. And that leads us to the question how to produce this non-alcoholic beer. And I brought you an overview, and we have different possibilities to produce non-alcoholic beers. It all starts in the brew house. And there we have different methods for producing the wort for our non-alcoholic beer. And one of the main backgrounds here is to reduce the sugar, because the yeast is reducing the sugar to carbon dioxide and ethanol. And the less sugar we have, the less ethanol or alcohol we will have in our non-alcoholic beer. So there are different meshing processes where we can just jump over alpha or beta amylases and then reduce our main sugar maltose, which is then not, I would say, there for our yeast to ferment. We have different production methods there. We can try to reduce some of wort-like aroma components during the wort boiling process, but the main focus here is set on our pH value. Normally, a beer has a pH value about between 4 and 4.5 pH value, and so we have to adjust the pH during our cooking process or during our meshing process. When we are done with that, we have two main differences in producing non-alcoholic beers. On the one side, we have biological methods. When I'm talking about biological methods, I mean that we have our wort, and this wort is fermented until we have an alcohol content below 0.5 volume percent. In Germany, the regulation there is that a non-alcoholic beer has to have less than 0.5 volume percent, and it's the same in the main of Europe. There are different methods, biological methods to do that, and they are all located on the fermentation cell. So one thing would be here that we have so-called discontinuous processes. And one of the main and oldest things would be a so-called stopped or limited fermentation, where I ferment at very low temperatures, which means that the metabolism of the yeast is set on a very low level. So the yeast will ferment less sugar than normal at normal temperatures. And when we're talking about stopped fermentation, we are talking about 1 to 5 degrees Celsius, where we ferment our wort. And then we ferment it until we reach an alcohol content about 0.3 to 0.5 volume percent. After that, the whole fermentation process has to be stopped by separation or filtration, and then we have our ready fermented beer. On the other side, we have so-called maltose negative special yeast. The main sugar for our yeast to ferment and to produce ethanol and carbon dioxide is maltose and maltotriose. And when I have a yeast which is not possible to produce that or to reduce this maltose, we can start with high temperatures where the yeast metabolism is higher. So this maltose negative yeast is producing a lot of valuable aromas like higher alcohols and esters. So maltose negative yeast beers are normally very fruity and have a more beer-like character than the original stop fermentation, because during the stop fermentation, metabolism is very low and the aroma content of beer-like aromas is very low too. There are different other methods, for example, continuous processes like the use of immobilized yeast. You can imagine that like a fermenter, where I have a continuous fermentation during the whole process. But they all have in common that I ferment wort up to 0.5 volume percent. And these non-alcoholic beers normally have a very sweet taste, and because there are a lot of sugars which are not fermented. And normally these kind of beers have to be pasteurized, because otherwise there would be the danger that in the bottle the beer could ferment and reach a content above 0.5 volume percent. And this is a thing we definitely don't want. On the other side, we have a different approach here, and this would be so-called physical processes. The main difference to the biological processes is that we have a normal beer, a normal fermented alcoholic beer, and then we are reducing or removing the alcohol. And this could be by two main processes. The first one would be so-called thermal processes, where we distill the alcohol out of our beer. Another process would be membrane processes, where we filter our ethanol through a membrane, and the ethanol is diffusing, and after that we have a non-alcoholic beer as well. Today, and because we did a lot, I would say, research together with Hofsteiner, we will focus on two production methods: on rectification on the thermal side and membrane processes on the reverse osmosis on the membrane process side. And maybe let's start with our thermal dealcoholization process. And the first thing is how can I describe it? And there's a special definition for thermal dealcoholization processes, and that means that I'm removing the ethanol from our finished fermented, ready fermented beer via distillation. And when you look at distillation, there could be a little problem, because normally ethanol has a boiling point around 78 degrees Celsius. And when I do that with my normal beer at 78 degrees Celsius, you could imagine that there would be some problems like a darker color and a not very pleasant aroma after that. So we will harm the beer a lot. And what can we do against it? We can use vacuum, because the lower our pressure is via vacuum, the lower is our boiling point of ethanol. And that's why we reduce our pressure to reduce this boiling point, and then we have a lower impact on our beer. We will not have an impact on our color, and the best part would be that we have a lower impact for aroma components, because there's a little problem with thermal dealcoholization processes. Due to the process, we are losing a lot of different aroma components, which has a similar boiling point than ethanol, because it's all a distilling process. And we have here on our left side our mother beer, our original fermented alcoholic beer, and on the right side I brought you some data about a non-alcoholic beer. We reduced here, you can see that we reduced the ethanol content a lot, but we will lose a lot of different aroma components. And a very important thing for us brewers is to reduce the maximum of alcohol with a minimum reduction of our typical beer flavors. And there are different approaches, which I will show you in the next slides. Nowadays, there are four main dealcoholization methods. When we look at the thermal dealcoholization processes, it all started with a classic vacuum falling film evaporation. We have spinning cone columns. These devices are used a lot for the dealcoholization of wine, for example. And then we have classic rectification columns, which are state-of-the-art nowadays. And we have different approaches like evaporation. But today we will just focus on the rectification. And when we look at our rectification, we can define it as a cascade-like sequential connection of evaporation and condensation under vacuum. And when you look here on the right side, we have our beer, and the first process is that we have to degas this. If we don't degas our beer, we would have the problem that in the rectification column we have a vacuum, right? And if you have carbon dioxide, a lot of carbon dioxide in your beer, there would be a lot of foam building. And then we have a very bad separation of the ethanol during our rectification. We don't want that, because after that you have to clean this rectification column a lot. We did some trials with that in our chair or on our chair, and I can tell you it does not make the least of fun to clean a rectification column because of foam building. So we degassed our beer. During that process, carbon dioxide and the first aroma components are leaving our beer, because a lot of aroma components are diffusing in our vapor stream of the carbon dioxide and then are lost. The degassed beer went to our rectification column, and there are some processes or some steps. And the first step is that we have a separation of our whole component mixture over several stages. Here we are talking about different columns in our rectification. And the liquid and vapor flow is countercurrent for enhanced mass and heat exchange. So we can see here that during our rectification column, a lot of vapor is produced. Here it's called Brüden, or here in English vapor. And in this vapor, all of my ethanol and most of the aroma components is bound or diffused. And in the second step, we can reduce the aroma, or we can separate a lot of the aroma components from our ethanol vapor. And we can do that with a so-called condensation process, where the temperature is lowered a little bit beneath the boiling point of my ethanol. So the ethanol is condensing, and all the aroma components which have a little bit higher boiling points than ethanol, they are still in my vapor stream and can be saved for later processes. And this aroma concentrated vapor is sent to a so-called aroma recovery. And in this aroma recovery, the temperature is lowered below the boiling point of these aroma components. So I will get a liquid, a so-called aroma water, where a lot of these aroma components is found. And then later it can be blended back to my non-alcoholic beer. Because after the rectification column, I will get the non-alcoholic beer with almost no aroma. And it can be blended back here with the aroma water, but this aroma water has 2 to 6 volume percent of ethanol, and that could be a problem which I will tell you later a little bit. Here we can see the step of the aroma recovery, and if you have questions about it, I will be pleased to answer them later. So the goal here is to lower my aroma losses while I'm producing a good non-alcoholic beer. So here the main focus would be, I would say, the quality, like we talked at the beginning. When I'm looking at my evaporation process and at the aroma recovery in special, I have higher condenser temperatures, and then I have a higher ethanol aroma concentration in my aromatic water, and I can influence this process with different techniques. For example, if I have a higher reflux of my vapor, I can save more aroma, but I will get more alcohol in my aroma water. So sooner or later there would be a problem to produce non-alcoholic beer the higher my reflux gets. So we want to try to have a very low reflux there. When I look at my non-alcoholic beer, it has a special flavor. A flavor, maybe at the beginning to talk about it, is the consumption of all my aroma components I have in my beer and of my mouthfeel, which I have while I'm drinking that beer. So the flavor here is a very acidic beer normally, because most of the aroma components are reduced, and these aroma components normally mask my acidity of my beer. And if these aroma components are not there, the acidity is a little bit higher. A completely dealcoholized beer has a very grainy malt-like character and, like I said, this acidity. I would say that rectification processes or evaporation processes like this are state of the art and one of the most used dealcoholization processes when looking on the physical dealcoholization side, because it has a lot of advantages, like I can use my aroma recovery and then can blend the aroma back to my non-alcoholic beer. A very positive side is that it's a continuous process. If I want to dealcoholize a lot of non-alcoholic beer, I can do it especially with this rectification device, because I can produce non-alcoholic beer 7 days a week, and that in a continuous process. Another positive side is, due to the distillation process, I can reduce the ethanol content below 0.05. And if we reach that point, we are talking about a so-called 0.0 beer. I would say in the US and in Europe, this is a very big trend to produce this 0.0 beers, and you can simply produce them with this rectification device. But there are a few downsides. The one thing is, of course, we can lower our temperature, we can lower our boiling point with vacuum, of course, but there will still be a temperature stress. So if you will not adjust your rectification column right, you will get this temperature stress in your beer, and then later you might have some, I would say, temperature-induced aroma components, which will taste a little bit honey-like, bread-like, and you want to reduce that a little bit. We still have a high loss of alcohols and esters, and this is due to the, I would say, distillation process, of course, but like I said, we can save some of these aroma components due to our aroma recovery and then blend it back to our non-alcoholic beer. At our chair, Brewing Beverage Technology and Pricing, we have a thermal dealcoholization device, a rectification column, and we have a rectification column on industrial scale. And I don't know if you ever saw distillation column for non-alcoholic beer, and then you will see these devices are very big. They're up to 6 meters high, and they need a lot of space in your brewery. So a high space is required for this dealcoholization process. If you produce 0.0 beers, there could be the problem that the aroma recovery is not suitable for that, because, like you can see here, you still have 2 to 6 volume percents of ethanol in your aroma water. And if you blend that back for a 0.0 beer, you would have the problem that reaches alcohol contents above 0.05 volume percent. So other techniques have to be developed there. That's everything about a very short sum up about rectification devices. And then let's look on another physical dealcoholization device, the so-called reverse osmosis. And the principle here is that we have normally in the nature, if you have a membrane and you have on the one side, you have a fluid with a very high concentration, for example, of ethanol, on the other side, you have a fluid with a very low concentration of ethanol, as an example. Normally, you want to have, or if you have this membrane on both sides, the nature wants you to have the same content of ethanol or the same content of solutes in your solution, right? And then something would happen normally that fluid from the side with the lower concentration will flow through the membrane on your side with your higher concentration, and sooner or later you will have the same concentration of your solutes on both sides. And we can do that for non-alcoholic beer, but then we would have water on both sides, and we don't want that. So what are we doing? There is some osmotic pressure due to this flow, and we want to overcome this pressure. So we are reversing this osmotic pressure with putting pressure higher, this osmotic pressure on the concentrated side. So we have a reversal of our osmotic flow, and so we can reduce this ethanol, because the ethanol will flow through our membrane on the permeate side. On this side, we have our beer, or our fluid with the higher concentration of ethanol, and the membrane is built so that only ethanol and water on the best part, or best side, will flow through this pores, and after that we can have a good dealcoholization process. A very good thing here is that higher alcohols and a lot of esters, they can permeate through this membrane as well, but we will see later that a lot of these aromas will stay on my non-filtrated, or my so-called retentate side. Let's look on a typical dealcoholization process with reverse osmosis, and this process can be divided in two, or more or less three parts. The first part would be a classical reverse osmosis process where we concentrate our fluid. So on the first part, which will be here, the orange marked part in this graph, there we can see that we will reducing our volume of our beer, and then we have an increasing of alcohol, aromas, extract, etc. pp. And in the second step, after we reach our highest concentration degree, we can start with our dealfiltration process. If we would continue with our concentration, we would concentrate and concentrate unless we have, or until we have no beer left. You can use this processes, for example, for producing orange juice extract as an example, but normally we don't want to have that for our beer. So in the second step, after we reach our desired concentration degree, we start with our dealfiltration. And if you look at here, we can see that we are putting in dealfiltration water, which will be deaerated brewing water, and the flow of this water is the same like the loss we have here with our permeate, so the volume will be the same. And during that process, this is the, I would say, the real dealcoholization process, because during this dealfiltration process, we are washing the ethanol through our membrane with the degassed water out of our system. And the longer I dealfiltrate, the lower my ethanol content gets. You can see it here that the alcohol content gets lower and lower with the time. After we reach our desired alcohol content, which will be normally, we believe, 0.5 volume %, we have a high concentrated and very aromatic dealcoholized retentate, I would say. Normally, this retentate is very bitter and very intense in aroma, so it's not desirable to sell that as a beer. So in the third step, we are blending that with degassed water to a desired, I would say, extract. And with this blended retentate, we have finally our completely dealcoholized and blended beer, which has all the desired values you want to have. After that, we have to carbonize our beer, and then it's ready for pasteurization, and then after that, sell. Let's talk on the last slide of the aroma of these beers. On the right side here, I have two graphs. On the left graph, you can see the retentate, the dealcoholized beer, and on the right side, you can see the permeate. And you can see that some of the aroma components will not diffuse as much with other components through our membrane. So the upside of this dealcoholization process is that we have a high concentration of beer aroma components in our finished beers. Aroma components which have different similar properties like my ethanol or same polarity, we will lose during our dealcoholization process. For example, there is dimethylsulfide, which has this corn-like character in beer, and we will lose that completely during our dealcoholization process. And there are a few things I can set on my dealcoholization device to reduce that aroma loss. One thing could, for example, be that I'm playing with my temperature. If I increase the temperature during my filtration process, I will save time because more ethanol will diffuse through my membrane faster. But on the other side, the higher my temperature is, the more aroma I will lose. Another thing would be the flux, the flow of my permeate. If I increase it, I will have a higher retention and I will save some time. But when you look at the membrane, you will have a blocking on the retentate side, a so-called biofouling. And that could lead to higher cleaning processes, which will be intense and a little bit more expensive. Another thing could be the pressure. If I increase the pressure, I can save retention time. I can save time, and I will have a higher retention of my aroma components in my retentate. But cleaning would be a little bit difficult there as well. And another very important thing is, of course, the target alcohol content. We talked about the thermal dealcoholization process, where we have the positive effect that we can produce 0.0 beers very easily. We can produce 0.0 beers with reverse osmosis processes also, but I need a lot more time. And the longer I dealcoholize, or the longer the dealfiltration process will be, the more aroma I will lose. So there are some up and some downsides with this process, which I will show you here. So we will dealcoholize at very low temperatures, about 5 to 15 degrees of Celsius. And with these low temperatures, I don't have a thermal impact on my beer. So this whole dealcoholization process is very gentle for my beer. Another thing is, like you can see at these two graphs, is that we have a very high aroma concentration. We have some losses, but they're not as big as thermal processes if I look only at the rectification. And another thing would be that a reverse osmosis plant is smaller than a rectification column. There are a few downsides, of course, like with every device. Nowadays, state of the art, we are producing non-alcoholic beers with reverse osmosis only on a batch wise. So we need a lot more time. The energy costs are higher, and we cannot produce as much non-alcoholic beers as with rectification columns. We are using polyamide membrane for reverse osmosis processes, and this membrane needs special cleaning devices, special cleaning agents, which are more expensive than the cleaning agents for my thermal dealcoholized beer. And we talked about the second step, the dealfiltration step, where I'm pumping water in my system, and that leads often to a very watery mouthfeel in my ready dealcoholized beer. And the main question we can ask us here is, how can we get a beer with a very high fullness and a very good mouthfeel, and how can we improve this? And with this steps, I'm already done with the dealcoholization. I think now it's your turn, Sandro. If you have any questions later, I will be here and I will be happy to answer them.
Thank you very much, Sönke. Very interesting and very detailed. You are a real expert at the university about producing non-alcoholic beers. That's why we chose you to do a project together. And I would like to give you some insights of this project.
Okay.
Okay, see you soon.
See you soon.
Okay, so yeah, together with Sönke and his team, we made some trials, but these trials that I show right now, they were even done previously. So we had it I have to do a short flashback to 2017, where we made our first trials together with the TU Munich. And at that time, we only could use the thermal dealcoholization, not the reverse osmosis. And the question was, is there any hop product that fits ideally to the base beer prior to dealcoholization? And at that time, we checked different things like, so we used always the P90 beer as a reference, so which means this beer was exclusively brewed with P90 pellets at the beginning of boiling. We used 100% total resin extract, then in addition, the P90 beer together with some tannin extract. So here we increased the amount of polyphenols, and we also used xanthoflav extract to increase xanthoumol, but also especially the hard resin fractions. In all these beers, we also had a late hop dosage towards the end of boiling. And as we just learned, not only in our trials, but also from Sönke's first slides right now, the whole aroma was evaporated, so there's no chance to get any hop aroma into a non-alcoholic beer that is afterwards treated like this. So, but still we had to look on the taste of these beers, and with regard to the taste, there was already a slight tendency that the usage of an extract could be of advantage. We wanted to double check this, that's why we did some more trials together with Sönke in 2022. And besides the thermal evaporation, we also wanted to focus on the reverse osmosis. And the question was, is there any conventional hop product that fits ideally to the base beer before you do the non-alcoholic beer out of that base beer? The products that we used in this trial was the pellets type 90 again as a reference. Then we also used CO2 extract and total resin extract. So these are the two extract types. You see it's a little bit different from the starting material, also the extraction solvents that I use. So no extraction solvents, of course, in case of the type 90 pellets. So in case of the type 90 pellets, this is the fingerprint of the used hop variety, and everything is inside each fraction and substance group. Whereas in the CO2 extract, you primarily extract the hop oils and the soft resins. There are no polyphenols or other components inside. And the difference between these two extracts is that with the ethanol, you also extract all the unspecified hard and soft resins. So this is a little bit closer to the variety specific composition comparing to the pellet type 90, which is the fingerprint. You can see these are the products that we have used for our trials. All of the products were made from the variety Palatao Polaris from the crop year 21. And starting with almost 20% in the type 90 pellet, you had a high increase here for the CO2 extract up to 60%, and almost 53% in case of the total resin extract. But if you have a look on the difference between the lead conductance value, which is let's say the total amount of bitterness in a certain product, you see a bigger difference here in case of the total resin extract compared to the CO2 extract. So this already gives you analytically the information that there's more than alpha acids inside. And talking about these different extracts, just two more slides about it. You see that using a different extraction solvent results in a completely different product. So on the left side, you see the total resin extract that has a very good solubility in water or in wort, because the polarity is much better here, whereas the CO2 extract is rather unpolar and it needs a certain time to get dissolved in the wort. That's why you need a more intense boiling and maybe even a longer boiling time to reach the same yield. But it strongly depends on the brew house, so there is not necessarily a difference in yield. In case of, as you see it from the picture already, there's also a different taste, obviously. This is controversially discussed. The ones prefer the one product, the others prefer another product. It also depends how much you look into the variety characteristics and are they of importance or not. And there are a couple of considerations to be made for the one or the other extract, and please feel free to ask us for our handout that we have made about it. Picking up a study from 2015 from Dr. Dresel, he determined hard resin components, and he characterized them, and he also determined the taste and the thresholds of these single components for the first time. And this was quite interesting, especially this re-engineering experiment where there was a Pilsner beer as a reference. So, and using a zero beer that was unhopped, the bitter scale was on a very low level, of course, because there was no hops inside. Adding the equal amount of iso-alpha acids, you already increase the bitter intensity, and by adding all the substances that he had found to be relevant for the overall bitter taste, you came almost on the same level of the Pilsner reference beer, which means it's more than iso-alpha acids in the beer, and this is the main conclusion that is given here. And keeping in mind this issue, the choice of extract makes a difference when it comes to these considerations. Jumping back to the trials that we have performed together with the Technical University at the Chair of Brewing Technology of Professor Becker, we produced 3 different lager beers, each differently hopped with the conventional products that are introduced, the type 90 pellet, total resin extract, and CO2 extract. And all of those beers were exclusively hopped at the beginning of boiling because we only wanted to focus on the taste impact and not on the aroma. We wanted to achieve about 16 to 18 milligram per liter isoalpha acid, so respectively similar amounts of in case of IBUs, and we made a standard fermentation with the standard yeast W3470. From these 3 brews that we have performed, we chose both dealcoholization techniques that are available at the chair, so either the thermal dealcoholization and the reverse osmosis. And then from these 2 strains, we again we kept the beer as it came out, so as a 0-0 beer, but we also made some blendings with a mother beer to achieve an amount close below 0.5%, which is the definition of alcohol-free beer in Germany. I know there are different definitions across the globe, and whenever you have the chance to use the mother beer to give back some body to the beer, it's always a good possibility. But if you don't have the chance to add back some of those of the base beer, you have to consider other possibilities how to improve mouthfeel, flavor, and aroma. So in the end, we came out with 12 different non-alcoholic beers that were intensely investigated after bottling and pasteurization. So we had a tasting that was of the fresh samples of 2 different panels. So the panel at Weihenstephan and also the panel on our side here, our internal panel. And besides a lot of analysis that we have performed, I would like to show you the analysis results of the staling components of the fresh and the forced aged samples. So these are an extract of the analytical results of the base beers and the corresponding non-alcoholic beers with 0.0 alcohol. You see from the base beer that all of the base beers were pretty close together with regard to original gravity, alcohol by volume, pH as well, and also the isoalpha acids that we wanted to achieve came out in the non-alcoholic beers exactly in the range that was the target. So close to 18 here and close to 16 here. So you can compare the bitter intensity and the taste of these beers quite well. Interestingly, here also the pH drops a little bit down after thermal evaporation, whereas it remains stable or gets a little bit higher in case of reverse osmosis, as you can see from the data here. Yeah, we had, coming to the results already, we had 2 tasting panels, as I mentioned. For the results, I have to point out we made a lot of tastings with different attributes that were asked, but in the end, we had to make a final scoring about all the results. And sometimes the scoring results, they are only 1/10 in between to get either the first or second place, or to be on the third or the second or the third place. So, but in the end, the overall results are as they are, and I would like to show you what came out. So we had the 2 panels, we had the rankings of the different beers, and having a look on the 0.0 beers, you see them on the left side, 0.5 beers on the right side, and the same for the reverse osmosis. Something that was a little bit more obvious in our case, we have found that the P90 beers were, in the case of the panel 1, were mostly ranked on the lowest place, whereas it was ranked on the first place for this beer. But also in the case of the panel number 2, the pellet type 90 beers were never on the first place at all, 2 times on the second place and 2 times on the third place. So overall, you can say the pellet beers were ranked on a little bit lower level, whereas the extract beers were ranked always on the first or second place in case of the panel number 1, as you can see here, except for this 1 single beer. And for the panel number 2, there was also a clear tendency towards the total resin extract that was ranked on the highest score for all the beers that we have made. Having a look on those beers analytically, we checked the aging components fresh and after forced aging. So on the left side you have the fresh samples, on the right side you have the forced aged samples, and for the pellet beers it looked like this. So jumping from an initial value around 100 micrograms per liter, after forced aging the pellet beers jump to more or less 300 micrograms per liter, and the same for the reverse osmosis. They come from 200 and reach almost 400 micrograms per liter. So this means there's an increase that is more or less the same, independent from the technique, but the starting point is a little bit different. I cannot completely explain why we have 100 micrograms per liter here in between the two techniques. I assume it's about the pilot scale trials that we have performed there. So I can imagine that in commercial scale, you wouldn't find that difference at all. However, having a look on the other products like the CO2 extract here first, you find similar ranges in case of the fresh beers, except this one. I guess this is an outlier. And here for the extract beers in comparison to the pellet beers, you already find a little bit lower values for the CO2 extract. That is even confirmed with the total resin extract. So they are either on a similar or same level or even a little bit lower. But you can say for all of those performed analysis, the extract beers seems to be on a lower level after forced aging. And in overall, putting all the numbers together, we find the pellet beers increase during forced aging roughly about 200 micrograms per liter, whereas the hop extract beers only increase from 100 to 170 micrograms per liter. So there seems to be a certain tendency towards the extracts. So what are the messages to take home? Yeah, from our point of view, from the tasting results, the extract beers seem to be of more advantage compared to the beers that were produced with pellets exclusively. I have to point out it's also a feedback that I get from time to time from our customers. So not only our pilot scale results, also commercial trials or productions seem to have the same tendency. With regard to the used technology, there's no, the forced aging, that the increase was on the same level, although they started on a different basis. However, there's no big advantage of the one or the other technology. But what we have seen in this forced aging trials, that the level of the aging components of the pellets were higher already in the beginning and also in the end. So might be a tendency towards less flavor stability in case of pellets. And picking up this, and we have published all this in the EBC and in the Brewing and Beverage Industry Journal, so you can find the papers also on our website and to pick it up. Talking about flavor stability, 2 more slides about how you can improve it and what are the possibilities. So when we talk about flavor stability and aroma, it's always a question about masking effects. Not always, but one big issue is also the masking effects. And you have the formation of saline components over time in the beer, that's clear. And generally you say hop flavor increases the flavor stability in a certain way. The question is also why. And there's a certain masking effect when you have a hop aroma in the beer, and consequently you higher the thresholds of the aging components, so they cannot come through so easily. So you can camouflage certain aging that starts from the day one. Trials that were performed were also published by Stefan Hanke, for example. Here he published about trials where beers were hopped on different stages. So starting at Sweetwort and to the Whirlpool, and of course all those beers had very low levels of linalool, which is the blue marking here, and the acceptance of the aged beer was, let's say, 40 to 60%. So consumers did or not did drink that beer, but for the beers that were that were hopped on the later during the hot side of beer production, and consequently had also a certain aroma. You see a much higher acceptance of plus 80 to 80%. So those beers were aged in the same way, but due to the fact that they had a hop aroma, you could mask the aging components and you could increase the flavor stability and acceptance finally. And talking about non-alcoholic beers and what kind of hop aromas can be dissolved in those beers, it's also a question of solubility, because usually ethanol is a very good solvent for hop aromas, but in case of NABs it looks a little bit different. And we made some trials recently where we focused on different amounts of ethanol and we checked which aroma components can be transferred to the beer. And in this trial, we also had one part that was focusing on 0.5 beers. So we had 0.5% of ethanol in these beers. And as a conclusion for those beers, we have found that the terpene alcohols are very good soluble in those beers. Esters and ketones are rather good soluble, but mono and sesquiterpenes like myrcene, cariphyllene, and so on are hardly soluble in those beers. So it's rather tricky to put such components into a non-alcoholic beer. And using this this knowledge, we have specifically designed hop products as well to put only the substances into those products that are also soluble in the non-alcoholic beer. So we have the whole here this is the overview about the families of hop oils that we have. So products like the type dry, they have primarily the mono and sesquiterpenes, so I wouldn't recommend to use those ones for the non-alcoholic beers. But the others, they are very soluble in beer, and especially the type selected contains those aromas that are easy soluble in non-alcoholic beer. And we have also chosen certain fractions and compositions that also improve a little bit the mouthfeel and also the flavor. Yeah, that's the possibility how to achieve more flavor stability, but also a hoppy flavor on a non-alcoholic beer. But as you have seen also in the first part of the presentation, it's also a question which kind of products you use in the base beer already prior to physical dealcoholization. Okay, so these are the messages I can give to you for today, and I'm curious about any questions and comments that you might have. Sönke, welcome you back.
Hi again.
Hi. I hope your mic is on.
I hope so.
Yeah.
Good. Breathe.
Okay, so I see the first question that is about pH, and depending on the technique, can you say something about what is it? I've shown already our results. Is this a typical behavior that you have seen from trials?
Yeah, I would say when we look at the thermal dealcoholization process, the concentration process there is a lot lower than, for example, for the reverse osmosis, because for thermal dealcoholization process we only lose 5%, which are the volume percent of ethanol. But for the reverse osmosis process, of course, we are concentrating, and therefore we have a higher concentration of, for example, different bitter acids, for example. And therefore we have a decreasing pH level.
Understand.
But with the blending later, we can adjust it, of course, as well.
Okay. And another question about the increase of IBUs. So as you just mentioned, you concentrate the non-alcoholic beer through any of these techniques. What is your expectation about how much should you reduce the hop dosage in the brew house prior to dealcoholization? So what is there any percentage that you can give for each technique?
I would say for thermal dealcoholization process, you can work with your normal beer or with your normal mother beer, but for the reverse osmosis process, you have this concentration step, and we measured bitter acids in permeate and retentate, and that was a little bit, it led to nowhere, because in the permeate there was no bitter acid, so it all remains on the retentate side. So we have a higher concentration there, and that means depending on the concentration step we want to have, we have to adjust maybe the bitter acid content in our original beer. Maybe a little bit lower bitter acids or a lower bitter content in our mother beer is better.
Yeah. but you can increase it on the downstream side anyway, just in case.
Of course.
Okay. Final question we have is about polyphenols and the influence of that. Of course, I've just shown that there's a difference between using pellets and extract. So maybe this is also a little bit the difference about the taste preferences and the aging. On the other hand, you have the polyphenols that come from the malt. Do you see this is a good screw to play around about mouthfeel and so on, or what do you think?
Yeah, good question. I would say, yeah, it possible is because the mouthfeel, if we have low aroma compounds, like for example for thermal dealcoholization trials or thermal dealcoholized beers, the mouthfeel normally is completely different compared to the mother beer. Yeah. The same is for a concentrated reverse osmosis beer, because of course the polyphenols and everything will remain on the retentate side. Good thing there is we have a higher foam stability, but maybe the mouthfeel is a little bit too heavy. On the first slide I showed you processes we can do in the brew house, so maybe try to start there and reducing or adjusting maybe the polyphenols there.
Yeah. Okay. So I don't see any more questions for today. I would say we are both available through the website to get contacted, or either Sönke to perform trials if you are planning more non-alcoholic beer recipe adjustments, and also from our side we'd be happy to support you with any kind of products and possibilities that we have. So it's time to close the session for today. Sönke, thank you very much. It was a very interesting seminar.
It's always nice to come to Hopsteiner, so thank you for inviting me.
You're welcome. Okay, everybody, see you to the next session, and thank you very much for your attention, and we stay in touch. Bye-bye. So,